Hello and welcome to another Reigate Maths video. This is Simon, and in this video we are looking at mechanics from the first year of the A-level maths content. In this video we're going to be looking in the Forces and Motions chapter specifically at Newton's third law. So Newton's third law is the law that states that when one body exerts a force on a second, the second body exerts a force equal in magnitude and opposite direction at the same time. So this is kind of your typical idea of equal and opposite forces. The best sort of example to talk about this is think about something on a table. Put a book on a table. The book does not fall through the table. Why? Well, the book is exerting a force on the table. It's its weight. So the weight being mg. The table pushes back on the book with a force R. We've already seen in previous videos the idea of a reaction force. In this case, there are no other forces going on. This reaction force is in the same plane as W. You can see they're in the same line of action. They're not at angles. It is perpendicular to the plane, the surface, because it's in the same direction as W. And it, in this case, is equal to W. We know it's not less. If r was less than w, then there would be acceleration. We know that from F equals ma, Newton's second law. So if r was smaller than w, the block would accelerate, or the book would accelerate through the table. If r was bigger than w, the box would accelerate up, which, well, if you put a book on a table and stare at it, clearly doesn't happen. The only other option is that they are the same. Now, if we start putting in extra forces, let's say we push down, now R is no longer equal to mg. R will increase because it has to match now the sum of the forces going down. Otherwise, again, the box would go through the table. And that's the idea of Newton's third law. It's really useful to use not only in questions like this, but in some examples that we're going to look at in a minute. One of the main sort of key applications of Newton's third law is when you look at a tow bar. So if you've got a car and a trailer, now I am not an artist, so this is a car and this is a trailer. They are joined together by a coupling or a tow cable. In this case, we have the car pulling the trailer along. And if it's accelerating, then the sum of the forces forward are going to be greater than the sum of the forces going backwards. But here, at this section, the forces must balance, because if they don't, what's going to happen? Well, the tow cable is going to stretch or it's going to snap, and we know that that shouldn't happen. So here we have two forces going in opposite directions that are the same. In this case, tensions, or if it's a coupling, a thrust. So what we're going to do now is we're going to have a look at a few examples of how to use Newton's third law. So in this example here, we've got two particles, P and Q, one with mass 6 and one with mass 4, connected by a light inextensible string at rest on a smooth horizontal surface. A horizontal force of magnitude F applies to the first particle in a direction away from Q, and when the string is taut, the particles move with acceleration 0.5 meters per second. Lots of information here, so let's do what we do best and summarize this in a diagram. So we've got a particle P and a particle Q. Now I don't know the dimensions of P and Q, but I know that P is bigger than Q, so I'm going to draw it bigger. We know P has mass 6 kilograms and Q has mass 4. So now we've got our sort of base diagram, what we need to do is start putting some forces on. So first off, it's at rest, and then the force is applied. So we've got a force of magnitude F applied to P, away from Q. So we know F's going this way. Now it's smooth, so there's no resistive forces, there's no friction. When the string is taut, the particles move. So the string is taut, which means we have tensions here. Each has its reaction force, and each has a weight. So I'm going to call the reaction force at P, RP, the reaction force at Q, RQ, because they are going to be different. Likewise, the weights I'm going to call WQ and WP. We don't necessarily need to do that, we can write down their values, but this is much more general, and in questions where you don't know what they are, it's useful to keep them general. We also know the whole system is accelerating at a rate of 0.5 meters per second squared. The key thing is that both particles are accelerating at the same rate at the same time. That's because the string is inextensible, which is actually what we're going to be talking about in part C. What that allows us to do for part A is ignore these two forces that are going to cancel out. So for part A, because we're interested in what this force is, not these ones, we're going to just treat the whole thing as one big block of mass 10. So we know forces forward, so F is going to equal mass times acceleration. So the mass of everything together, because they're accelerating at the same rate, the mass is 10, and we're told it's accelerating at 0.5 meters per second squared. So F is 5 newtons. What we've really done here is we've said, okay, forces forward are F and T. Forces backwards is T, so the T's cancel. So by considering this whole block as one thing, we've ignored the tension force here, because that's what we want to work out in part B. Now obviously we could work that one out first and use it to find F, but we do F first, and this is actually relatively straightforward. Now we want to find the tension. What we're going to do is we're going to consider exactly one of the blocks. So we're going to say, okay, well, I know here, for instance, this one, that F equals ma. So the forces, so F minus T, because I'm now ignoring Q, is going to be equal to 6 times 0.5. We know what F is. So T is 2 newtons. We could have done that using this block Q, which would have been quicker. See here we only have, the only force we have is T. So we have T equals M times A. 4 times 0.5 is 2. So either way is fine. Part C, so we've already discussed how we've talked about how we've used the fact the string is inextensible. It's both particles accelerate at the same time at the same rate. And the fact that it's light means we didn't have to include its weight in this calculation. Or its mass, more specifically. Okay, we didn't need to consider its mass for A or B, but A is more relevant. This topic is the first of, and some basic examples of, topics called connected particles. We're all talking about two particles that are joined together by a string. We're going to look at another example now that's very, very similar, talking about a car and a trailer. Then in the next video, we're going to make it specific to a system called pulleys. So here we have our example 2. A car of mass 1,200 kilograms is connected by a tow rope to the truck of mass 2,800 kilograms. A horizontal force of driving force D acts on the truck. Horizontal resistance forces of 800 newtons act on the car, and 600 newtons act on the truck. The car and the truck accelerate at 0.4 meters per second. So, what we're going to do first is we've already been given the diagram. It's very pretty, much better than the one I could have drawn. So we're going to label this now. So if you pause the video, have a go at labeling all of the forces yourselves, and then come back and we'll go through how to label them. So we know the car has mass 1,200 kilograms. So the car has weight 1,200 G, which means it has a reaction force, which I'm going to call RC. I know they're the same, but we actually don't need to worry about this in terms of our calculations. The tow truck has a mass of 2,800, and it has a reaction which I'm going to call RT. I don't like that because we're going to use T for tension, but T for truck's good enough. Again, this is actually irrelevant for this question because we're not going to need it. A driving force D acts on the truck, and then we've got two tensions here. The other thing is we have a resistance force of 800 acting on the car, and 600 on the truck. Now this is a bit of a pain to draw, so I'm just going to stick it here. Technically, we should ideally draw it connected to this truck. So I put my T in an awkward place there. But the diagram, because we're not being told to draw the diagram, it's given to us. This is just for us. So to find D, again, like we did in the first example, we're going to consider this whole thing as one big particle, so we can ignore the T's. So again, Newton's second law, F equals ma. So the forces forward are D. Forces backwards are this 600 resistive force and 800 resistive force. So D minus 800 plus 600. And that's going to equal to the total mass times the acceleration, which is 0.4, which I forgot to put on the diagram. There we go. So we know that D minus 1,400 is going to be equal to 4,000 times 0.4, 1,600, I believe. Let's just check it. So we've got 2,800 plus 1,200 times 0.4. Okay, good. I was right. So D is going to be 3,000 newtons. Which makes sense. You know, that seems like a really big force, and it is, but it's a truck. You know, trucks can exert a large force. They've got to be able to, otherwise they can't pull cars. So now we've involved this resistive force. Next year, so in the second year content, we extend this idea even further and say, okay, this resistive force, we're not going to tell you it's 800. We're going to tell you there's a friction, and we're going to give you this extra measure called the coefficient of friction that's going to allow you to work out the 800. And that's where these forces come into play. So that's why it's good now, although we don't use these in any way, it's useful to get used to drawing them on your diagram because you're going to need those next year. Part B, working out the tension, works exactly the same way as it did before. We consider one of the particles, either the truck or the car, and we go from there. Now in the first one we used the driving particle. In this one we're going to use the other one. So we know again F equals ma. The forward force on the car is T. The resistive force is 800. We know the mass is 1,200 and it's accelerating at a rate of 0.4. So T is 1,200 times 0.4, 480, plus 800 newtons, which is 1,280 newtons. If we did it using the tow truck, we would get exactly the same result. And that's the first part of Newton's third law. It's kind of, this idea does continue into the second year in the topic of connected particles, where we start doing this but putting it on a ramp and looking at how to do it on inclined planes. So that's where it does get more complicated. But these basic ideas of where all the forces are, we combine with what you're going to do next year, ideas with friction and working at angles, to make this a more complete question. Thank you for watching.